session. So, you guys have heard about IXPE, that's a X-ray imaging polarimetry telescope that was launched in 2019. So, the telescope observed this gamma ray binary. Gamma ray binary means uh, a star with a binary system which emits gamma rays normally, like high energy rays. And the uh, binary in this system is a uh, neutron star, a pulsar. So that's why the name is PSR B15 B12 final 63. So uh, the paper introduces by starting to tell us about particle acceleration and uh, in relativistic shocks, how do they occur? Because in this paper, they have studied the boundary between the star's uh, shock and the pulsar's wind nebulae. So they two meet at a point, creating a shock. So uh, at that at that point, what kind of interaction occurs? That is their idea. So uh, the observation was done using IXP, like I said. So the observation was taken 16 days before and 13 days after the periastron. Periastron means the closest the pulsar gets to the star. The star here is a BE star, a very big, huge star. Uh, so IXP works using linear X-ray polarization by imaging the tracks of the photoelectrons. That's how the instrument works. And in this para, they say how much, uh, like how many observation seconds they got, and which detectors they used, and how they cleaned the data. And in the results, they in the fig one you can see the results. The flux is shown on the y-axis, and the days from periastron is shown on the x-axis. And uh, you can see a flare up and it is going down. So the flux increases when it is coming near, the pulsar is coming near, not near, like, near the uh, BE star, and it decreases. And you can also see it from SWIFT XRT telescope that also recorded the same. Then they used a algorithm called PQ algorithm. That is the standard for IXP. So they observed that the polarization is 7.9 degree. This one, 7.9 degree of the total observed flux, and it is 5 sigma confidence level. So they are sure that the 8 percentage, 7.9 plus or minus 1.4 is definitely polarized, and the electric vector polarization position angle is minus 41 degree. That measures how we are looking at the source electric vector position angle. So we are at the surface and it is like tilted to the downward direction 41 degrees, something like that we can imagine. So then they used Stokes parameters to see the same result, and they got the same margin of results. They also performed spectroscopic analysis using XPEC. So they used three different ways to see how much the uh, uh, how much polarized is the light from the X-ray light is from this source, and they all lead to the conclusion that it is around 8, and the EVPA the electric vector position angle is around minus 43. And it is within a confidence level, so they are sure about that. But they are not sure if this percentage is varying or not, because the data is only these few days, so they could not figure it out if this 8% varies over time or not. So moving to the discussion section, with these properties, one can say that there is a momentum ratio. No, there's a momentum ratio. Uh, if you take that, you can check if the cone is shaped towards the pulsar or to the star. Here, the cone is open towards the pulsar with a bow shock to the star. That means it looks in figure 3, like the yellow lines. That's how the bow shock looks like. So in figure 3, the circle is periastron, and the diamond and the squares are the places where they measured these observations. And for synchrotron emission, EVPA should be perpendicular to the magnetic field. So here it is true when we look at the geometry. So they are sure that this is produced by synchrotron emission. Then poloidal field geometry can also produce this kind of uh, effect, but there is no sufficient information that it can produce that. Also, then they checked uh, the compactness with another gamma ray binary called LS5039. So, based on the simulation and comparing it with this one, they would say that the orbital separation is about 500 light seconds. So that's the uh, distance, and based on this, the time scale of the X-ray emissions can be said to be 200 seconds. And when it is passing, uh, so then they say that the low magnetization, like only 8% is magnetized. So they say that magnetization is less than 10 raised to minus 3. So they say that it is because efficient production of X-rays. Due to the low magnetization, the production of X-rays are efficient. Then
okay, time's up.
time's up. I think the paper is up. They say that the main point of this paper is that magnetic field geometry in a gamma ray binary is uh, discussed, and they figure out that the acceleration region is aligned perpendicular to the shock cone axis.
Okay, any questions, comments? So in figure 3, what's the time scale of the movement?
It's days, the given days here, 16 days and 13 days.
From here, so the first point to the last point.
Yeah,
16 days?
yeah.
Okay. Doesn't that, if it's moving along the orbit, doesn't that change the polarization angle too?
That is discussed, but it did not change massively. So
What's the range? So
you can see.
they show the polarization angle as a function of time, no?
No, they did not show that polarization angle is a function of time. they show here as a function of time, they take in this paragraph, they take the observation first half and the second half and see how it varies. And there is a variation like 11% of light was polarized and UVPA is different. And here it is 3 and 42 when on the second half. So, but based on the Q values, that Stokes parameters, they cannot uh, conclusively say that of variability.
Okay. So maybe variability. Okay. Any other questions, comments? So what's the overall picture of the field? So the measurement for one gamma ray binary.
Yes.
Then what's the overall goal?
The overall goal idea is that we have never measured what is gamma ray, polarized gamma ray from a X-ray binary or gamma ray binary. I mean, so this paper proves that those emissions are also polarized in some percentage.
Okay. Thank you very much. So shall I move on? Who wants to go next? According to this, John. Yeah. You want to go next?
Yeah, sure.
You want to talk about it?
I think I put them both in a spreadsheet and Facebook group.
Are the immune for variations of cell population?
Yes.
Okay.
Okay, so today I'm going to talk about azimuthal variation of stellar populations in Bar galaxy. So in this paper, basically they're using a manga survey to investigate the stellar population, especially in the Bar. So, yes, so they also analysis like the stellar mass density and also their metallicity, like within the bar, and then trying to see what the property of the bar is, and then how they affect the galaxy evolution. Okay. So, so from here, oh, sorry. So from here, they are taking their data, their image from manga survey, and they took out about 10,000 unique galaxies, and it's in a median redshift. So the redshift is around 0.04. Yes, and then they have like two subsets of samples. So if the galaxy they have a coverage like out to 1.5 effective radius, they call it primary. And then for the 2.5 effective radius, they call it secondary because their resolution is slightly like worse. Okay, so like the actual resolution corresponding to this redshift can is about 1.8 kiloparsecs. And then for to identify the bar, they are also they are taking two like main models. So one is for fitting the stellar populations of all the galaxies. So they are using the manga surveys pipeline. So they are using like this so-called miles and then the INF models to fit all the stellar populations within this galaxy. And then for the to take out the bar, they are using the famous Galaxy Zoo. So they are like cross-fitting the data in Galaxy Zoo and the manga survey. So they claim that for each galaxy, there are at least 15 volunteers to visually inspect this galaxy, and then also they mark out like which part can be identified as the bar. And then after all, they are using all this data and then guess about like 1,300 galaxies. Okay. So from here, since their aim is to study the bars, so they only selected all those galaxies that have a significant features. Yes, and then they also shows the overall the star formation rate versus the stellar mass plan. Yes. And so here we can jump to their analysis. So this is one of the example, like how they process the image. So from here we can also see that they are like identify where is the bar region and also the spiral and also the stars and the center of the galaxy. And then what I think the special part is that they're trying to normalize all the galaxy's data. So from here we can see here is the overall results. So what they did is that they put um, they put all the bars like as the x-axis, and then their length, like since like each galaxy may have different lengths of the bar, like all set normalize the bars equals to 1. So you can compare the like overall results of all the samples.
How did you classify bar region and spiral region?
I'm sorry?
How did you separate in figure 3? How did you select the orange region?
You mean separate the bar or?
Yes, in figure 3, yes.
You mean in figure 3? I think one is that they are taking like they're taking the bars data from Galaxy Zoo because inside they have.
Galaxy Zoo is just classification, right?
Yes.
So how did you decide the orange region?
So it's basically by visual inspection.
By eye?
Yes. So I think from Galaxy Zoo they asked the volunteer to select. Yeah, it's from manga image. Yeah, it's not. But they are like combining Galaxy Zoo data.
I know, but then
Yeah.
the orange region is decided in this paper, not Galaxy Zoo, right?
Think I think it's the design. They are directly using the Galaxy Zoo, like for the B, like the caption B, they are say like drawing from Galaxy Zoo 3D, including bars, spirals, and galaxy center.
So how did you do that?
I think, yeah, I just, yeah, they are just using the like a Galaxy Zoo's data.
Okay.
Yes. Okay.
I don't know how they did it, right?
Yeah. Okay. So for the results, like here's the okay. So here's the overall result, and then also like they make all these to do a normalize. They like turn all the galaxies like rotating anti-clockwise. So from the top panel to the lower one is the value of the age and metallicity and also the stellar mass density. Okay, so from here we can like obviously see that for like all of the sample, they tend to have a higher metallicity at the bar, and also corresponding to the like their stellar mass metallicity. Okay. And then after that, they're trying to investigate different subsets of the galaxy mass. So they divided them into 3 groups. So it's like their solar mass 10, like below 10 to a 10, and then between 10 to a 10 to 10 to a 11 and above. Okay. From here, so here is the results of different populations. So from here, we can also see that in terms of the stellar mass density, for the higher stellar mass galaxy, they tend to have a more clear structure of the bar. Yes, and then for the it's the lower panel. So it's the stellar mass.
Vertical or horizontal?
Yeah.
Which one?
So you mean
vertical or horizontal? Which one?
Means the horizontal one is the bar, like the red part.
Okay.
Yeah. So they have like a more clear division between like the bar and also like the interregion of the galaxy. So from here basically they find out okay, so basically they in this research like a key point is that they kind of confirm that the bar is like a long existing object, and then also they have a higher metallicity, and then by using the Manga survey data, they can constrain a more local condition in a bar, like in terms of the stellar mass density. And by doing so, like it may help to do more research in the star formation within this region. Yes. And then also, I think in the discussion, they also discussed like how the stellar population in the bars might migrate. Yes, they also, but I haven't like looked into the detail of like how they analysis all the kinematics about the bars. I mean, this is one of their focus. They're trying to explain like how the bars involve the whole galaxy evolution in terms of the kinematic. Yes. And then so for this paper, the most important takeaway is that they find bar tend to have higher stellar mass surface density compared to their surrounding disk, and they are metal-rich environment, which is also kind of consistent with the previous research.
Okay.
Yeah, okay.
Good. Okay, good summary. Any questions, comments?
I have a question. So about this conclusion, so bars of higher stellar mass density, that I can understand, but then I just wonder, by definition of bar, we expect this conclusion, no? Because in order to identify bar, we need to have more high stellar mass density. Otherwise, we cannot see structure.
Yes.
So therefore, I wonder this conclusion is just coming from their sample selection, no? Or just definition of bar.
Yes.
Maybe other point maybe more interesting, I guess.
That's a good point.
Oh.
Yeah.
Yeah, just maybe comment. Maybe.
Yeah.
Thank you.
Yeah. I think I completely agree that not just that, but all the conclusions are expected.
Yes. So I think like they're trying to like having a special resolution of the bar. I think that's what they're aim to do. So maybe yes.
So it's I think a good lesson for you or for us. Finding something new would be more interesting than
Yes.
confirming what's already known.
Yeah.
But that sounded good, so thank you very much.
Okay, thank you.
Any other questions?
Also,
Yes,
I also know how like the projected inclination involved to zero.
I think yes.
They just say somewhere like they have some
Right.
knowledge from previous
Yes.
but
I
they
think
didn't say it very clear.
but I do not like they eliminate the sample with too much high inclination. So
yes, but like how do they know this is 40 or 70 degrees?
yes. I'm not quite sure how they process with things. Yes.
they just remove something with not present. That's it. That's a present galaxy. There's no point. If it's inclined, you can do that because they still have 1,000 galaxies after we go this. Okay, then we move on to Simon. Accretion history of Milky Way.
Yes. So I've been reading on the accretion history. This is something new for me. I haven't learned this before, but I recently saw that there was a paper 4. I did not quite understand it. I think some of the results they used from previous papers, so I decided to go back to 1, and hopefully next week I talk about 2, and then 3, and then 4 in sequence. So in the broad picture, in the field of galactic archaeology, we want to know when and how our Milky Way formed, which parts formed where, and also dwarf galaxies, when did it infall into us. And so in this paper, they discovered that the half-life radius of globular clusters depend on their orbital pericenter and total energy, and that the Milky Way tides may explain this correlation, although in the paper I don't think they have a very strong argument for this, but they suggest this. They also suggest that the accretion epoch, so that means when they fell into our Milky Way, can be calibrated by this total orbital energy, and that this relationship is affecting all like the satellites and also from the other proposed mergers of the Milky Way, including the Kraken galaxy, the Gaia sausage, and the Sagittarius stellar systems that also fell into our Milky Way. And they believe that this correlation that they found can be used as other tools to further investigate the origins of these globular clusters and dwarfs, as well as the assembly history. So for the data, they use the Gaia EDR3. So that means they have a good sense of the orbital parameters from velocities and orbital radii. They also selected globular clusters that were studied previously from literature. I believe that in total, they have about 144. They further split their globular clusters into 2 types. First is the low surface brightness and the high surface brightness ones. When reading the paper, I wasn't quite understanding why they split into these 2, but because in the results, they didn't discuss much about the differences between the 2 galaxies. Rather, they discussed more about the intrinsicity of the, rather than the low surface but high surface. But for reference, this is the first figure they have shown, and they split into 2. The first thing that they discussed and calculated was whether there was a correlation between intrinsic and orbital parameters. I believe that was also studied in previous papers also. And this was found that yes, in general, there is a correlation between the intrinsic parameters, which is the half-life radius of globular clusters, and also the orbital parameters. In this case, is the galactic center distances, which is the distance between the globular cluster to the center of our galaxy. So there is a correlation between these two, and this most basically all the results are from the previous papers they've plotted onto here. Perhaps they also investigate if there is another tighter difference relation between these two relations, and they found yes, actually, a tighter relation is between the half-life radius and the pericenter instead of the galactic center distances. So the top panel is the data they selected from literature. This is all the data, and the bottom panel they selected those with eccentricity larger than 0.6. So it means that it's not circular; it's more elliptical. And these two, well, compared to before, first of all, they have a tighter relationship. Second of all, they find that the higher intrinsities have even more tighter relationship compared to these. Although there are still, as you can see over here, those that are the vertical, the vast polar structure dwarfs are still not exactly well constrained. And so from this, they suggest that perhaps because the pericenter means that the peridistance means that the closest distance to the galactic center, right? So maybe this is because the tidal differences, since the closer they are, that the smaller the half-life radius. So maybe because of tidal distance, effects, they strip gas and other mass from the dwarf, the globular clusters, and therefore they show a smaller half-life radius. So to investigate this, they also did simulations. This is simulation based on another author, but they all assumed a half-life radius of 5 parsecs. They put it into different orbits, pericenters, and see after 2 gigayears how they evolve. So this line is the line we see from previous here. And they show that at least for these objects, they quite fit. I'm not quite sure what the color code means. They also don't quite mention it in the paper. So I'm not quite sure about that. But at least they mention for these objects, for those that have higher eccentricities, because 2 gigayears, those that are higher eccentricities or higher, larger radius, also the number of orbits is lower, so they haven't had chances to be affected by the tidal effects as much as other objects. So which is why we don't quite see a trend as compared to the lower pericenter objects. Again, in this paper they don't really talk too much about the reason, but the matter of fact is that there is a relationship, and that they might be explained by tides, or there might be some other effects. They also, so since that we know that the periradius has to do with the half-life radius, and the periradius also has to do with the angular momentum. So let's also consider the angular momentum and the total energy of these objects. They've also plotted objects that have been associated from other mergers, so other structures. So this is the Kraken galaxy, the Kraken merger event. This is the bulge in the center, the disk of our galaxy, and other events that they have labeled and they have studied in previous studies. So the top panel shows the intrinsicity that's lower than 0.6, which is, and the line over here shows the circular orbits. So this makes sense, right? Because the lower intensity, it means circular orbits means that they fit close to the line, and these objects are higher intensity and therefore are lower to the line. So what they found out is that we can basically, from using the angular momentum, trace a history of these different infall objects, from the bulge, which is the oldest, then the kraken, which is over here, the green, the disk, and then the other objects, and it sort of goes down over here. And these vast polar structures lie around here, and also the dwarf galaxies and the globular clusters normally lie over here, which is triangle structures. So these suggest that the total energy may be a proxy of the infalling time. So maybe those that have lower energy, this is negative log, so lower energy may have meaning that they've been in the longest in our galaxy. So if we extrapolate, so the infall times of these, extrapolate the energy and the look back time, we see a good, we see that they predicted that the dwarfs might lie here, which is also where we see that the median value is here. So this, I have just one more slide left. So basically, what they find is that this is yet another. So in conclusion, the total energy versus the half-life radius also shows a tight relationship, given what we see before. So they will see that the energy decreases with the time elapsed into the halo. So perhaps this is something that could be used in the future studies, at least for papers 2, 3, and 4. I believe they also use the result from this, that most dwarfs are incomers into the Milky Way halo less than 3 gigayears, which is confirmed by their total energy and angular momentum. The vertical polar structure, which they've mentioned, I haven't had too much time to talk about this in this paper, in the time constraints, but they also discussed about why they exhibit different behaviors from other dwarfs. And that their intrinsic size, half-life radius, may have to do with how much shock they, tidal shocks they experience. Thank you.
Interesting. Question, comment, please. So did they set the mass of the globular cluster the same?
About the same range, yes. Yes.
So we don't have to worry about the mass dependence of the size and things.
I believe they have a section that they discussed in the data about the mass range. I believe they are quite consistent with each other.
Okay.
Yeah.
How did they derive the energy again?
I believe the energy is sorry. Yeah, they didn't explicitly talk about how they derive the energy, but I suspect is the potential plus the angular momentum. Or the
velocity?
Yeah, yes, the velocity, sorry.
In line of sight or?
Line of sight, or I'm not quite sure how they derive the energy from velocity, so the kinetic energy. They didn't explicitly say in the paper. That was also one of my questions I had, was how they got the energies. Given that it's negative, I'm sure that they have a potential component, but I'm not quite sure if it's the line of sight or if it's the proper motion of the velocities.
Okay, any other questions, comments?
I have a quick question.
Yes.
I think this is also interesting to me, and also this is very new to me. But in figure 3, I just wonder if they discuss any potential observation bias. I'm not sure if there is a significant bias or not. Say, if you go to more distant globular cluster, maybe it is more difficult to find smaller sites because you cannot resolve it.
Yes.
I'm not sure where this observation limit comes. in this figure, then if
Mhm.
we are missing very small radius at the longer distance, then this
Yes.
may mimic this correlation, right?
Yes.
Therefore, I just wonder if they discuss this kind of observation effect.
I don't think they've discussed it in the paper. I might need to double check. I don't think this discussed in this paper.
I see.
Yeah.
I don't know if we can resolve, say, for example, 1 parsec at the size of 1 parsec, plus 1 parsec size, at, say, for example, 10 kiloparsec or so.
Yeah.
Can we resolve? I'm sorry, I cannot calculate.
Yeah, I'm not quite sure too. This is also very new for me.
But it's a simple triangle, right? So we should be able to calculate this angle.
Yeah. I mean, if in doubt, we can always build a bigger and better telescope. And
Yes. Okay. Maybe at least we can say there's no big one at nearby distance.
Yeah.
That's maybe for sure. Okay. Thank you very much.
Thank you.
Okay, good point. Any other questions, comments? Okay, if not, thank you, Samuel, for good summary. We look forward to paper 2, 3, 4.
Yeah.
Because one's interesting, so maybe 2, 3, 4 is also interesting. Okay, then it's a little bit early, but then who wants to present tomorrow?
Already started.
You already signed up?
Yes.
So, Jay, you want to do it tomorrow?
Yes.
Jay
Oh, good. I mean, Lapo,
and me.
and then Terry. Oh, very good. Very enthusiastic participants. Okay, so thank you very much. So we'll speak us today. Tomorrow we have Terry, Lapo, and Jay. Thank you again, and see you tomorrow.
Thank you.
Bye-bye.
Bye. Bye-bye, Tomo-san.
Good.